I'm a postdoc at NIST in Boulder, Colorado. My name is Ryan, and today I'm not going to be talking about superconductivity research exactly, but I am going to be talking about a topic um, that is important for cryocooler users. So this is a source of free cooling from cryocooler regenerators. And we're sharing this research because we think it's important for users of Cryocooler to know about. My outline. Pulse tube refrigerators have a large source of free cooling that is available, but in many cases underutilized or not fully understood. So our motivation behind this research is that utilization of this cooling source enables larger quantum information systems or reduces the required size of cryocoolers for current cooling applications. So why should this audience in particular care about this research? Well, first of all, I can tell you exactly how to cool many coaxial cables, for example, down to your base operating temperature. And I can tell you exactly how to, say, cool or condense 1 millimole per second of helium-3 for free. So I'll actually tell you how to do these things in this presentation. And also this is good background to have when communicating with cryocooler or dilution refrigerator manufacturers. That's why you should care. And then the actual content of this talk will be, first I'll explain why there is this free source of intermediate cooling from regenerators. I'll talk about two applications, those I've already mentioned, cooling coaxial cables down to base temperature and then cooling returning helium-3 in a dilution refrigerator. And then I'll briefly touch on a model for predicting temperature of heat absorption. So let's talk about this free source of cooling that pulse tube manufacturers don't advertise. Here's a pulse tube refrigerator, and everything in black that you see on the slide, this is what the manufacturer is going to tell you about. They're going to tell you there's this large helium-4 compressor. It requires a bunch of power and a bunch of water to cool it. And then they're going to tell you that it has a certain amount of cooling available at the first stage, say 50 watts at 50 Kelvin, and maybe 1 watt at 4 Kelvin at its second stage heat exchanger down here at the bottom. What they're not going to tell you is that there's a source of cooling available from this second stage regenerator, which is this tube I'm highlighting here. And the cooling available from this tube is actually quite large. It's about 2 watts at 7 Kelvin. And the amazing thing about this source of cooling is that it has no effect on the second stage cooling. So you can get 1 watt at 4 Kelvin, and you can also get 2 watts at 7 Kelvin. But this is something they don't tell you about. And the reason why this cooling is available is because the helium in this regenerator is operating in the real fluid regime. So let me get into that in a bit more detail. Why is there this free source of cooling? And to explain that, I have to introduce a concept called total power. And this is a schematic of our regenerator, that second stage regenerator I mentioned. It's operating between about 50 Kelvin here on the left and 3 Kelvin on the right. And total power is the amount of power that's flowing down this regenerator towards the cold heat exchanger. And if we do a first law analysis on this cold heat exchanger here, we see that total power directly subtracts from the cooling power available at 3 Kelvin. And in the real fluid regime, total power changes drastically. So here I'm showing, this is an oscillating fluid in this regenerator, and I'm showing the enthalpy changes in this oscillating fluid. In the ideal gas regime, usually enthalpy changes are only a function of temperature, but in the real fluid regime, there's also this pressure dependence to enthalpy. So there's this new term in the enthalpy flow that arises only when the fluid's operating in the real fluid regime. So I can cut to kind of the consequences of this. In the ideal gas regime, this T beta, which is up here on the right, beta is their thermal expansion coefficient, and T is the temperature. T beta equals 1 in an ideal gas, and this means that the total power flowing down this regenerator can usually be 0 in the ideal gas regime. And this leads to a cooling power equal to the acoustic power, or the PV power. In the real fluid regime, all of this changes. That's because T beta is changing dramatically, and T beta is near 0, or it approaches 0 near 2 to 3 Kelvin. So this means your total power flowing down this regenerator is now actually very big. Total power is approaching the acoustic power at these temperatures. And this means your cooling power also gets very small the colder the temperature is. So this T beta is approaching 0, so cooling power is a very small fraction of acoustic power at low temperatures. So the big takeaway from this slide, total power is very large in the real fluid regime, particularly below about 7 Kelvin. And this is a fixed loss on the system. So you can do a whole bunch of things to this regenerator, but as long as the minimum temperature in the regenerator is very small, there's this fixed loss on the cooling power. And we can look at this in a little bit more detail by analyzing the temperature profile in the regenerator. So this is what the temperature profile in one of these regenerators looks like. An interesting thing about the profile is that the gradient between 50 and 3 Kelvin is really concentrated towards the warm end. And you have a large portion of the regenerator at the minimum temperature in the regenerator, say 3 Kelvin here. And in an ideal, if the fluid was an ideal gas, you would expect a linear temperature gradient between 50 and 3 Kelvin. And to explain why there's this flattening of the temperature profile, you have to analyze this total power flow. So I've got an equation for total power flow, and I don't need to go into the details here, but what's important to know about this equation is that you have a bunch of terms that are dependent upon the mean temperature at a particular location, and then you also have some terms that are dependent upon the temperature gradient. And because these temperature dependent terms are so big, it forces the temperature gradient terms to adjust to that to these big temperature dependent terms. And that's because total power flow through this regenerator is constant. You're not applying heat or absorbing heat anywhere along the length of this regenerator, so total power is constant as a function of the axial position. So because the power is so big down at low temperatures, it forces the gradient to be very large in the beginning of the regenerator. And now let's look at what happens when we apply heat to the regenerator. So this is the new temperature profile with heat applied. And the most important thing here is that there's this portion of the curve that is still at the same temperature. So we applied intermediate heat about 2/3 of the way down the regenerator, but the temperature at the very end of the regenerator is unchanged. And as I mentioned on the previous slide, total power is only really a function of temperature. So there's this fixed loss, and that fixed loss is unchanged. So that means cooling power is unchanged. And if we look at a first law box of the place where we applied heat, we have the same total power leaving that first law box. We've got some heat that we applied going into the box. And that means that total power going into this first law box has now been decreased by the amount of heat that we applied. So what we see is that there's this, the temperature gradient at the warm end decreases in magnitude. So as a summary here, real fluid effects are a large loss fixed by the minimum temperature of the generator. And when we apply intermediate heat, we decrease power towards the warm end. So the degree of freedom required for all this to work is that the temperature gradient needs to have some flexibility at near the warm end. Okay, so now with that background, I can move on to some experimental results. And here is a picture of our experimental setup. What we have is a two-stage commercial pulse tube refrigerator. The smaller tube is the buffer tube, which is essentially just an empty tube between 3 Kelvin and room temperature. And this tube on the right is the regenerator. So this regenerator, we've actually applied a large amount of copper clamps to this regenerator. And these clamps are used to monitor temperature or to input heat. And the distance between our thermometers or between our heaters is 1.5 centimeters. So we have a very high spatial resolution measurement of the temperature profile. And we believe these are the highest resolution measurements of the pulse tube refrigerator regenerator ever taken. So let's actually get on to the experimental results. So on this slide, we're asking what happens when we apply intermediate heat to the regenerator. So we've got our cartoon on the top, and we've got the experimental observation on the bottom. So this graph is showing the temperature of the regenerator as a function of normalized axial position. And we're applying heat to this vertical line here. This Q dot int, that's where we apply intermediate heat. And the bottom curve is showing with no heat applied. The second curve is showing with 1 watt applied, and the top curve is with 2 watts applied. So something I talked about previously, we see that the minimum temperature in the regenerator is not disturbed. And based on our analysis, if this temperature is not disturbed, we expect cooling power at the cold end to stay fixed. And that's exactly what we see in this inset. We're plotting cooling power at 3 Kelvin as a function of intermediate heat. And the amazing thing here is that we apply 2 watts of heat to this regenerator. And the cooling power at 3 Kelvin barely changes at all. It's about 10 milliwatts. And also note that the intermediate heat we can apply is about an order of magnitude higher than the heat we can apply at 3 Kelvin. And also note, we predicted that this temperature gradient should decrease in magnitude at the warm end, and that's exactly what we see in the experimental data. So what we've done is we've done these type of experiments, but at many different heater locations and over a wider range of heat values. So that's what I'm showing here on the right. It's a cooling capacity map. And I'm plotting heater temperature versus intermediate heat with up to 3 watts applied to the regenerator. And so we can follow a particular curve, say this red curve here, we're looking at when you apply heat halfway down the regenerator, what temperature does that heater get to? With 0 watts applied, it's about 5 Kelvin. With 1 watt applied, it's 7 or 8 Kelvin. And with 2 watts applied, it's up to about 20 Kelvin. So the amazing thing about all this is, I mentioned before, cooling power at 3 Kelvin, you can apply heat to the regenerator at any of these locations. And for the most part, cooling changes very little at the cold end. So this is your free source of cooling. Okay, so now let's get on to applications of intermediate cooling. So these are things I want this audience in particular to know about, because there's essentially free cooling in your cryocooler. So I'm not sure if the manufacturers of your cryocoolers are using this cooling yet, but if they're not, let's talk about what they could be doing. So the first application is a conductive heat load. So really what I'm talking about here is a bunch of electrical cables that you need to cool down to the base temperature of your refrigerator. So I've got a picture here on the right. This is from a commercial dilution refrigerator that we have here at NIST. And these cables need to be cooled eventually down to the base temperature in the refrigerator. And we've talked to users of these cryocoolers, and something that they're unsure about is where they should be heat sinking these cables. So, you want to use this free source of cooling to remove some of the heat load at your second stage heat exchanger. And you know that you can use the regenerator to do this, but you're not sure where you should heat sink these cables. So that's what we're exploring here in these experiments. So what we've done is we've developed a heat conduction model, assuming a certain type of coaxial cable. And then we're going to input the measurements that I showed previously to predict what load will be on the second stage heat exchanger. And we're going to try to minimize that load. And I'll cut to the chase. If you choose the right place to heat sink the cables, you can cool 50 cables with zero effect on the second stage cooling power. And to do that, we'll look at this data here. So all of this data is a function of heatsink placement. And if you heatsink nearer the warm end, those are data points towards the left. And if you heatsink nearer the cold end, those are data points towards the right. So the top subplot is showing the temperature of heat rejection, or sorry, the temperature of the heatsink. And if you heatsink nearer the warm end, you have a higher temperature for your heatsink, of course. And what that leads to is a larger amount of heat conducted down to your second stage heat exchanger. So the second subplot is showing the drop in cooling power at the second stage heat exchanger. And that heat is being directly conducted down these coax cables. So essentially, it's a bad idea to heatsink too close to the warm end. You can lose 50% or more of your cooling power at 3 Kelvin just because of these cables. And then the third subplot is showing a different effect. This is the drop in cooling at 3 Kelvin directly from applying intermediate cooling. So you can't apply these heat sinks too close to the cold end, or some of that heat is directly absorbed by the cold heat exchanger. And if you take these two effects and combine them, what you get is a really nice optimal location. So if you heat sink these cables about 3/4 of the way down the regenerator, what you get is about zero drop in cooling at 3 Kelvin. So there's this optimal location. And this is the kind of information we're trying to disseminate to cryocooler users like you. Okay, so our second application is cooling or condensing helium-3 in a dilution refrigerator cycle. This is actually already being done in some DR cycles. We've got a picture here at the right of a dilution refrigerator we have at NIST. And this tube on the right is the second stage heat exchanger. And what you'll see is there's this tube brazed onto the outside of this regenerator. So what they're doing is they're actually using the cooling available along the regenerator to pre-cool this helium-3 before you send it to the second stage heat exchanger. And the problem with how this is being done right now is that we don't believe that people really know the best way to do this. And what we have is a very good experiment to answer the question, what is the best way to do this? How much helium-3 can you flow down this regenerator, etc. So the goals of this study are going to be to find how much helium-3 this regenerator can cool, find locations where heat exchange is most critical if you wrap your regenerator like this, and also find the best helium-3 line configuration. So by that I mean you could actually wrap this heat exchanger in different ways around this regenerator. And what's the best way to do that? And our experiment's suited to do this because we can apply heat wherever we want to along this regenerator. So we could turn all 10 of these heaters on, we could turn only the last 5 heaters on, etc., etc. So what we're going to do is we're going to actually do experiments, but we're going to simulate the heat exchange as if helium-3 was flowing down this regenerator towards the 3 Kelvin plate. And we're going to assume perfect heat exchange here. So here's the results of these helium-3 simulations. At the top left, we're showing intermediate heat as a function of normalized axial position. So, and we're showing this for 2 different curves. We have a 1 millimole per second line and a 2 millimole per second line. So this is where the heat is being dumped along the regenerator at different helium-3 flow rates. And in general, we see that most of the heat is being dumped near the middle of the regenerator. So if I were designing a heat exchanger, I'd want to make sure that that heat exchanger was most effective near the center of the regenerator. And on the right here, we're looking at some data as a function of the molar flow rate. So the top two plots are showing if the helium is going to exit this regenerator heat exchanger as a fluid or as a gas or a liquid. So we can follow these blue lines here. These are if you wrap this heat exchanger around the entire regenerator. And we see that up to flow rates of 1.8 millimoles per second, we can actually condense the helium on the heat exchanger on the regenerator. So the exit temperature is below 3.18 Kelvin, and the quality of the helium there is 1. That is, it is a liquid at a flow rate of 1.8 millimoles per second. And this bottom subplot, we're showing the drop in cooling power at the 3 Kelvin plate. So this is essentially what you pay for this helium-3 flow rate. And at this very high helium-3 flow rate, you were only paying 10% of the cooling power at 3 Kelvin. And you can compare this to this dashed black line here on the left. This is if you didn't use regenerator cooling, how much helium-3 you could condense. You see you could condense about really very small helium-3 flow rate. And you're going to use up all of your cooling power at 3 Kelvin to do that. So we've done this at many different heat exchanger configurations. That's what this table here is showing. I don't have time to talk about this, but we've tested a whole bunch of different ways to wrap this heat exchanger around the regenerator. And the reason why this experiment is important is because really what most people will want to do in practice is they want to do some combination of cooling loads. So they want to have some type of conductive load like electrical cables, and they might have to heat sink this in the middle of the regenerator. So that might change the way they can wrap this helium-3 line around the regenerator. So experiments like this are very important for investigating combined cooling loads. Okay, so I have just 2 slides on a model for predicting the temperature of heat absorption. I'll go over this pretty briefly. So what we have here on the right is some data for heater temperature versus intermediate heat. This is something I've showed previously. And what I'm showing here now is the results of our model for predicting this heater temperature. So we've got our data on the dashed line and the model that we've developed in the solid line. And qualitatively, our model does very well for matching the experimental data. And what we're doing with this model is we're predicting the temperature of heat absorption, and we're also predicting this change in sensitivity. You can see that for the first 2 watts of heat applied, the heater temperature is relatively insensitive, and then there's a dramatic increase in the sensitivity. So why should we even care about this model? First of all, it's critical for any thermal integration technique. If you want to do things like that coax cable experiment, you have to know how the temperature of your heater will respond. And second of all, this model is easily scaled to your particular cryocooler. So it has nothing to do with the cryocooler we've developed. It can be easily modified to your cryocooler. So I'm just going to briefly explain how the model works. At the top middle here, I'm showing the data for how the temperature profile changes as we apply intermediate heat. And in general, what we see is that this temperature profile is translating towards the cold end, the more heat that we apply to the regenerator. And actually what happens is once this profile reaches the location of heat injection, that's when we get this sharp change in sensitivity for heater temperature. So there's this blue portion of the curve where the gradient is not near the heat injection location. And then once this curve sharply transitions, that's when the profile is near the heat injection location. So what we've done is we've developed this model in 2 parts. At low temperatures, we only consider real fluid and finite heat capacity changes to total power. So we use these 2 derivatives to develop this bottom part of the model. At high temperatures, we estimate the temperature profile using a Taylor series expansion, and the equations for this expansion are given here. I don't have time to talk about it, but essentially we solve for the curvature and gradient of a downward facing parabola using energy conservation. So there's some takeaways from this model. First of all, this model reveals strategies to actually increase the amount of available intermediate cooling. And this model is applicable to any generic pulse tube refrigerator. And it serves as a framework for more complicated cooling applications, such as combined single point injection heat, combined single point heat injections and distributed heat injections. Okay, so let's conclude here. The second stage regenerator of cryocoolers can provide multiple watts of cooling, and this source of cooling is free. It doesn't affect the cooling power at very low temperatures, and it's very big. It's actually 10 times more than the cooling available at 3 Kelvin. And this source of cooling is available because of real fluid effects, and so it's only available when you're operating your cryocooler at very cold temperatures, say when the cold tip's less than about 7 Kelvin. We showed that you can cool many coaxial cables. You can cool 50 cables to 3 Kelvin with no consequence to second stage cooling, but the location of that heat sinking is critical. And then we showed you can cool a large amount of helium-3 for a dilution refrigerator cycle, and we identified the highest amount of flow rate before the temperature of the pulse tube refrigerator would rise. So essentially, we just want to get this information out there because we believe all cryogenic systems should be using this resource of cooling. And we're doing all of this because improved thermal integration will enable larger quantum information systems, or will enable smaller cryocoolers to fulfill current cooling needs. So thank you everyone for listening.
Thank you very much, Ryan, for a really clear and interesting talk on a topic that I know very little about, I'm afraid.